Good evening, students. Biochemistry Simplified. Again, Madam Win here. Thanks for the subscriptions, thanks for the likes, thanks for the views. Still together we can. As we keep on learning, I appreciate every step you people are making. So, after looking at fatty acid degradation, it's handy to finish with fatty acid synthesis and finally finish on ketone bodies. Fatty acid synthesis. Remember, degradation already took place in the inner mitochondrial membrane, and we generated the acetyl-CoAs. And we need those acetyl-CoAs for synthesis of the fatty acids in the cytosol. Still, the importance of the organelles, very important. Without those organelles, we can't understand much of the chemical reactions. So, we are going to look at fatty acid synthesis, and I mentioned that there is an interaction. All these pathways are interrelated in some way or another. In this case, the NADPH is needed for synthesis of fatty acids, and it will come from the pentose phosphate pathway, the pathway in carbohydrate metabolism. Remember, so they need one another. So it occurs mainly in the liver and adipocytes, and even in mammary glands during lactation. That is when fatty acid synthesis takes place. It occurs in the cytoplasm. If you talk about the cells, we talk about the cytoplasm, we talk about the cytosol. They are related in one way or another. So this fatty acid synthesis takes place in the cytosol. So the transport of acetyl-CoA into the cytosol from the mitochondria where it was. So it still needs a transport system where the citrate will come in as a transport system. It has to transport the acetyl-CoA, you can see in the figure here, from the mitochondria where the degradation took place, and it has to cross to the cytosol for the synthesis to take place. So, first, it has three stages in fatty acid synthesis. We have to transport the acetyl-CoA into the cytosol from the mitochondria, and we need the citrate transport system. And at that point, the NADH is also converted to NADPH. Then secondly, second stage, carboxylation of acetyl-CoA takes place. So another carbon has to be added. And then lastly, assembly of the fatty acid chain. So the sources of NADPH from fatty acid synthesis has to come from the pentose phosphate pathway. Not any other pathway will do that. And then there has to be a transport system to transport our acetyl-CoA from the mitochondria to the cytosol. So we talked about the carboxylation, addition of a carbon, and it's going to form malonyl-CoA. The enzyme being acetyl-CoA carboxylase. The first stage was we have to transport our acetyl-CoA from the mitochondria to the cytosol. Then the second step was carboxylation of acetyl-CoA. Then the third step is now when the synthesis of the longer chain takes place. So there we are also going to find the 5 steps which are involved. Just as the beta oxidation, carnitine has to transfer the activated fatty acid into the mitochondrial membrane. At this point, we have to start carboxylation of acetyl-CoA has to take place before we start lengthening or we start synthesizing our chain of fatty acid. So carboxylation takes place. The enzyme is acetyl-CoA carboxylase, and it is the regulatory enzyme. You can see biotin still a vitamin of the B complexes, very important. Biotin is vitamin B7, I think, to be precise. So it's also needed for this enzyme to work. That's how important vitamins are. It doesn't mean that we didn't discuss much about the vitamins and the minerals, but biochemistry is wide, bit by bit. We shall cover that. But that's how important they are, the vitamins. At the active site of the enzyme, they also have to be present. In this case, biotin has to be present for carboxylation. For acetyl-CoA takes place. It involves these 5 steps: loading of the precursors via the ester derivatives, and then secondly condensation of those precursors. And now in degradation it was oxidation. In this case it is reduction. In degradation it was hydration. In this case it is dehydration. And now we have even second reduction. The other side we had second oxidation. So in fatty acid synthesis we have opposite of whatever we are having in oxidation. So loading of the precursors via the ester derivatives involves much the elongation process of the fatty acid. So the acetyl-CoA, which had been transferred from the mitochondria to the cytosol, now we have an acyl carrier protein, the ACP, which you're seeing there. You have to add it to the acetyl-CoA and it forms acetyl ACP. We are removing the CoSH group. The malonyl-CoA, which was formed in the previous step by carboxylation of acetyl-CoA, also we have to add the acyl carrier protein ACP to form the malonyl ACP. These two are the ones which are going to the next step of condensation of the precursors. So the next step, condensation of those two, acetyl ACP and malonyl ACP. So it is going to form a 5. It was supposed to form a 5 product, carbon product, sorry, but there is a decarboxylation there. There is a removal of ACP from the acetyl ACP, and there is a removal of 1 carbon. Because you can see malonyl ACP had 3 carbons, sorry. Acetyl ACP had 2 carbons, so 2 plus 5 was bringing it to 5. But then acetoacetyl ACP is 4 carbons because decarboxylation has taken place at the point where condensation was taking place. So we are condensing the 2 precursors. The enzyme is acyl malonyl ACP, condensing enzyme. Condensation step takes place there. You're already synthesizing the elongation of the fatty acid chain. Then reduction takes place in the next step, where the acetoacetyl ACP is going through reduction process and we are forming 3-hydroxybutyryl ACP. The NADPH from the pentose phosphate pathway is used to form NADP+. The enzyme is ACP reductase. Now the next step is dehydration, removal of water from the 3-hydroxybutyryl ACP. The enzyme takes the name from the substrate 3-hydroxyacyl ACP dehydratase, removal of water, only at that 1 carbon. And when water is removed, crotonyl ACP has a double bond. It is formed. Then the last reduction step takes place. NADPH used from the pentose phosphate pathway. The enzyme is still enoyl ACP reductase, reduction process to form butyryl ACP. So it proceeds the same story. You can see condensation, reduction, dehydration, reduction. Again, it proceeds until you lengthen to the desired number of fatty acid you want. So rounds of synthesis continue until you have the C16, if you want palmitate, palmitoyl ACP forming. But then you have to remove the ACP because already your work is done. By addition of water, you form palmitate, the enzyme being thioesterases. Esterases. We are talking much about group specificity, the ester bonds. That is fatty acid biosynthesis. So the condensation products, you can see the precursors forming, malonyl coming this side, acetyl ACP coming this side, then they are going to form acetyl ACP, hydroxybutyryl, crotonyl, butyryl ACP, and then lastly you form your desired fatty